Just look up at the night sky on a clear evening, and you might catch a faint, hazy patch of light in the constellation Ursa Major, the Great Bear. That soft glow is the Pinwheel Galaxy, floating 21 million light-years away from us. It's one of the most stunning and photogenic galaxies we've ever observed, a sprawling cosmic pinwheel spinning gracefully through the blackness of space. But what if I told you that this beautiful, seemingly peaceful galaxy holds secrets so strange, so baffling, that they've left astronomers utterly mystified? We aren't just talking about beautiful swirls of stars and gas. We're talking about phenomena that defy our current understanding of physics, events that challenge everything we think we know about how the universe works. Welcome, friends. Today, we're setting off on a journey, one that will take us deep into the heart of the Pinwheel Galaxy, through its glittering arms and radiant core, to explore not just its beauty, but its deepest, most bewildering mysteries. We'll be uncovering 30 of the most unusual and unexplained occurrences ever documented in this corner of the cosmos. From sudden, violent bursts of energy with no clear source, to strange structures that shouldn't exist according to our models, to eerie silences where we expected cosmic chatter, each of these phenomena tells a story. A story of how much we still have to learn, and how the universe continues to surprise, humble, and astonish us. So settle in, open your mind, and get ready to see the Pinwheel Galaxy in a whole new light. This isn't just a tour of cosmic eye candy. It's an invitation to witness the edges of human knowledge, to stand beside scientists as they grapple with questions that have no easy answers. By the time we're done, you'll understand why this gorgeous spiral isn't just a pretty face, it's one of the most intriguing puzzle boxes the universe has ever placed within our view. Let's begin. Our journey into the strange begins with what might be the galaxy's most fundamental missing piece. In the heart of almost every large galaxy, including our own Milky Way, astronomers find a supermassive black hole, a gravitational monster weighing millions or even billions of times more than our Sun. These colossal entities are thought to be the anchors around which galaxies themselves are built, their immense gravity dictating the motion of stars and shaping the cosmic environment. So when we turn our most powerful telescopes toward the brilliant core of the Pinwheel Galaxy, we expect to find one. And yet, despite it being a textbook example of a grand design spiral, one of the largest and most perfect of its kind, the evidence for a central supermassive black hole is conspicuously, bafflingly absent. The search hasn't been for lack of trying. Scientists have meticulously studied the movements of stars and gas clouds swirling around the galactic center. The speed of these objects should betray the hidden mass of a black hole, like leaves caught in a whirlpool revealing the drain at its center. But in the Pinwheel Galaxy, the motions just don't add up. There's no gravitational signature, no telltale shudder in the fabric of spacetime that points to a lurking giant. It's as if the engine room of this magnificent cosmic ship is completely empty. This presents a profound puzzle that has spawned several compelling theories. One possibility is that the black hole was there but was somehow ejected. Imagine a scenario where two galaxies merged, each with its own central black hole. As these black holes danced around each other, they could have emitted such powerful ripples in space-time gravitational waves that the resulting kick sent the newly merged black hole hurling out of the galaxy entirely, a cosmic outcast drifting into the intergalactic void. Another idea is that the black hole isn't gone, but is simply dormant and hidden from our view. Perhaps it's in a quiet phase, not actively consuming enough material to produce the bright radiation we typically use to detect such objects. It's sleeping, and we haven't yet found a way to hear it snore. Perhaps the most intriguing possibility is that the black hole is fundamentally different. Maybe it falls into a new, unknown class of object that doesn't interact with its surroundings in the ways our current models predict. The absence at the heart of the Pinwheel Galaxy forces us to question the very foundation of our understanding. It suggests that the relationship between a galaxy and its central black hole might be more complex and varied than we ever imagined, and that for all its breathtaking beauty, this galaxy is playing by a different set of rules. Moving outward from the silent heart of the galaxy, we encounter a visible structural oddity that is just as bewildering. The Pinwheel Galaxy is celebrated as the quintessential grand design spiral, a perfect cosmic whirlpool. But a longer, more critical look reveals that this perfection is an illusion. Its majestic arms are not the symmetrical, balanced structure we see in textbooks. They are strangely and fundamentally lopsided. One side of the galaxy appears dramatically more defined, bursting with the brilliant blue light of young stars and glowing pink nebulae. The opposite side, however, seems comparatively faint, fragmented, and almost languid in its structure. This isn't a minor imperfection, it's a glaring asymmetry that challenges our models of how such beautiful spirals form and endure. In a stable, isolated spiral galaxy, the gravitational forces are balanced. The arms should be relatively even, wrapping around the core in a harmonious pattern. The stark imbalance we see in the Pinwheel Galaxy is a colossal sign that something has recently happened, a gravitational disturbance that violently upset this delicate equilibrium. The leading theory points to a galactic collision or a very close encounter with a smaller neighbor. Picture a stone thrown into a still pond. The ripples it creates are not perfect circles. They are interacting waves, some higher and some lower. A gravitational jolt from a passing dwarf galaxy could have sent a powerful density wave crashing through the pinwheel's disk, compressing gas and triggering a firestorm of star formation on one side while leaving the other relatively undisturbed. We may even be witnessing the aftermath of the pinwheel consuming a smaller galaxy, with the remnants of that cosmic feast still settling into their new home, distorting the symmetry in the process. Yet another, more mysterious possibility involves the invisible scaffolding of the galaxy itself, dark matter. We cannot see dark matter, but we know it's there by its gravitational influence. It forms a massive halo around galaxies, dictating how the visible matter moves and collects. What if the dark matter halo surrounding the pinwheel is itself uneven? An irregular, lopsided distribution of this invisible material would create a gravitational field that is stronger in one region than another. This would pull more gas and dust into that area, fueling an intense period of star birth and creating that sharply defined, brilliant arm, while the other side, starved of the same gravitational pull, would appear more diffuse and quiet. This idea is particularly compelling because it suggests the very fabric of the galaxy, its unseen foundation, might be crooked. This asymmetry is more than a curiosity, it's a live laboratory. The overdeveloped arm offers astronomers a front-row seat to the process of intense star formation, allowing them to study the life cycles of stellar nurseries in extreme detail. Conversely, the underdeveloped arm serves as a control for what the galaxy might have looked like before the disruption. By comparing the two, scientists can piece together the timeline of the event that caused this lopsidedness. The evidence is written in the stars themselves: the age of stellar clusters, the motion of gas clouds, and the distribution of elements all serve as clues in this cosmic detective story. The Pinwheel Galaxy's beautiful imbalance is a permanent record of a violent past, a reminder that even the most serene-looking objects in the cosmos are dynamic and ever-changing, shaped by forces both seen and unseen. Now, our investigation into the strange takes a turn from the grand, structural mysteries of the galaxy to the tale of a single, solitary traveler. Hurtling through one of the pinwheel's spiral arms at a speed so immense it defies easy comprehension, astronomers have identified a true cosmic outlaw, a hypervelocity runaway star. This isn't just a star moving quickly, it's an object traveling at thousands of kilometers per second, a velocity so great that it could easily escape the gravitational pull of the entire galaxy itself. Spotting such an object is like finding a single, incredibly powerful speedboat racing across a vast, calm ocean, and its very existence demands a dramatic explanation. The prevailing theory for such celestial renegades involves a cosmic catapult event, most often a supernova explosion within a binary star system. Imagine two stars locked in a mutual gravitational dance orbiting a common center of mass. If one of them is massive enough to end its life in a supernova, the sudden, asymmetric detonation can literally blow the partner star away like a gravitational slingshot, hurling it into the void at a staggering fraction of the speed of light. The runaway star becomes a surviving witness to its companion's violent death, forever carrying the momentum of that cataclysm. This is a well-established, though rare, mechanism within our own galaxy. But the plot thickens considerably when we consider the specific environment of the pinwheel. This hypervelocity star's trajectory and incredible speed have led some scientists to propose an even more exotic origin story, that it might not be a native of the Pinwheel Galaxy at all. It's possible this star is an interloper, a visitor from another galaxy entirely. In the crowded confines of a galaxy cluster, tidal forces during close encounters between galaxies can sometimes rip stars from their homes and fling them into intergalactic space. This star could be one such castaway, now just passing through the pinwheel on a journey that began millions of light years away. We are essentially looking at a celestial nomad, a drifter whose path has temporarily crossed ours. Determining its true origin is a monumental challenge that rests on precise measurements of its composition and its radial velocity, the speed at which it's moving directly toward or away from us. If its metallicity, the abundance of elements heavier than hydrogen and helium, matches that of other stars in the pinwheel, the supernova slingshot theory gains weight. If, however, its chemical signature is distinctly foreign, it would provide compelling evidence for an extragalactic origin, making it a rare and valuable specimen from beyond our galactic neighborhood. Each scenario unlocks a different piece of astrophysics, offering a unique window into the most violent processes that shape our universe, from the deaths of stars to the gravitational dynamics of entire galaxies. This lone wanderer is a messenger, and its story, written in its speed and its light, is one we are only just beginning to translate. But our exploration of the Pinwheel Galaxy's strange nature doesn't end with the visible stars and gas. It extends into the realm of the completely invisible, to the very fabric that holds the galaxy together. Surrounding its luminous spiral disk is a vast spherical halo of dark matter, an unseen gravitational anchor that is, by all accounts, behaving very strangely. Based on the motions of stars and gas within the galaxy, astronomers have been able to weigh this dark matter halo, and what they've found is deeply puzzling. It is far more massive than any standard cosmological model predicts for a galaxy of the pinwheel size and type. Not only is it unexpectedly heavy, but its distribution is also highly irregular and lopsided, a finding that clashes with our fundamental understanding of how dark matter should behave. This invisible halo is supposed to be the galaxy's foundation. According to our most successful models of the universe, the lambda-cold dark matter model, dark matter particles are cold, meaning they move slowly and they only interact through gravity. This should cause them to settle into a smooth, symmetric, and overwhelmingly large halo that dwarfs the visible galaxy. The pinwheel's halo defies this expectation on almost every level. Its irregular shape suggests a turbulent and dynamic history, one that the current simulations simply cannot replicate. It's as if we've discovered the foundation of a famous building is not made of solid, uniform concrete, but of a strange, shifting material that clumps and disperses in ways we can't explain. This profound discrepancy forces astronomers to consider some truly radical possibilities. The first is that we are witnessing the ongoing aftermath of a galactic merger. The gravitational pull from a smaller galaxy that was consumed by the pinwheel in the distant past could have stirred up the dark matter, disturbing its smooth distribution and creating the clumpy, asymmetric halo we detect today. The debris from this cosmic feast would still be settling, its gravitational echo permanently imprinted on the dark matter. Another, even more extraordinary idea is that dark matter isn't as simple or as cold as we think. Perhaps these mysterious particles can interact with each other through some unknown force beyond gravity, a type of dark physics that allows them to collide, scatter, and form complex structures within the halo. This would mean dark matter has a rich, hidden life of its own, a subatomic drama playing out on a galactic scale. There's also a compelling third option, that the pinwheel's dark matter halo isn't isolated at all. It might be dynamically interacting with the halos of other, smaller galaxies in its local group. These invisible halos could be stretching and distorting each other through gravity, like invisible hands molding clay, creating the irregular shapes we infer. This would mean we cannot understand the pinwheel in isolation. We must see it as the central node in a complex web of dark matter that connects it to all its neighbors. Unraveling this mystery is more than an academic exercise. The properties of dark matter dictate how galaxies form, how they evolve, and ultimately what fate awaits them. The Pinwheel Galaxy, with its inexplicably massive and misshapen halo, has become a critical testing ground for our most fundamental theories about the nature of the universe itself. Its invisible secrets may hold the key to rewriting the rules of cosmology. But the gravitational oddities surrounding the Pinwheel Galaxy extend far beyond its own lopsided dark matter halo, pointing toward an even more elusive and colossal presence lurking in the void beside it. The galaxy's rotation curve, a graph that plots the orbital speed of stars and gas against their distance from the center, tells a story that our eyes cannot see. In a typical spiral galaxy like our own, we expect stars on the outer edges to move more slowly, just as Pluto orbits the Sun far more sluggishly than Mercury. Yet the pinwheel's outer stars are whipping around at velocities that are simply too fast. They should be flung out into the intergalactic void, but something immense and invisible is holding them in a powerful gravitational embrace, preventing the galaxy from spinning itself apart. The sheer amount of extra mass required to account for this motion is staggering, far more than what can be explained by the pinwheel's own inflated dark matter halo. This has led astronomers to a breathtaking and almost unnerving conclusion. The Pinwheel Galaxy is not alone. It appears to be dancing with a companion, a ghost. The evidence suggests it is gravitationally bound to a massive, dark galaxy, an object with the mass of a large dwarf galaxy, but composed almost entirely of dark matter, with few, if any, stars to give it away. This invisible partner exerts a tremendous pull on M101, distorting its rotation and likely contributing to the violent asymmetry of its spiral arms. We are essentially inferring the existence of an entire galaxy by the shadow it casts, a cosmic phantom revealed only by its gravitational footprint. This idea of a dark galaxy challenges one of our most fundamental assumptions about the universe, that where there is significant mass, stars will eventually form. This dark companion seems to defy that principle entirely. One theory posits that it could be a proto-galaxy, a primordial clump of dark matter and gas that somehow failed to ignite star formation, a stillborn galaxy frozen in time from the early universe. Alternatively, it might be a galaxy that was stripped bare. A close encounter with the pinwheel in the distant past could have gravitationally ripped away all of its stars and visible gas, leaving behind only its dense, dark matter skeleton, a galactic ghost that continues to haunt its former partner. The hunt for this invisible titan is one of the most delicate tasks in modern astronomy. Researchers meticulously map the subtle gravitational distortions on the far reaches of the pinwheel's disk, searching for any telltale sign of a concentrated mass tugging at the fabric of spacetime. They also scan the area in multiple wavelengths from radio to X-ray, hoping to catch the faintest emission from any residual gas or the rare, ancient star that might have been left behind. Confirming its existence would be a monumental discovery, providing the first direct evidence for a new, hidden class of galaxy that has long been predicted by cosmological models but never conclusively found. It would force us to completely rethink the processes of galactic formation and evolution, revealing a universe where the luminous galaxies we see are just the glittering tip of a vast, dark iceberg. This profound silence at the very heart of the Pinwheel Galaxy presents yet another layer to its mystery. After the puzzle of its missing supermassive black hole, we encounter an equally baffling characteristic. Its center is unusually, almost eerily quiet. In most grand spiral galaxies, the core is a raging inferno of activity. It's typically a place of frantic star birth, crowded with stellar nurseries, and often anchored by an active galactic nucleus, a brilliantly luminous region powered by a supermassive black hole greedily feeding on surrounding material. The Pinwheel Galaxy, for all its splendor, displays none of this expected drama. Its core is a calm and relatively dim expanse, showing remarkably little recent star formation and no detectable signs of an active nucleus. This tranquility is deeply abnormal, making its galactic center a place of absence rather than action. So what could cause such a profound quiet? Astronomers are investigating several compelling possibilities, each pointing to a different chapter in the galaxy's history. The first and most straightforward explanation is simple starvation. For a galactic center to light up, it requires a constant influx of gas and dust flowing inward to fuel new stars or feed a central black hole. It's possible that the pinwheel has simply run out of gas, quite literally. The mechanisms that normally funnel this raw material toward the core may have broken down or been disrupted. Perhaps a past gravitational interaction with another galaxy stripped away the available fuel reserves, or maybe the complex dynamics within the galaxy's own disk are preventing gas from completing its journey inward, leaving the center to slowly wither in isolation. Another fascinating theory suggests the opposite problem, a feast that ended too quickly. It's possible the center did experience a massive, violent burst of activity in the relatively recent past on a cosmic timescale. This could have been a tremendous episode of star formation that consumed all the available gas in a single, furious rush, creating a generation of stars all at once. Following such a ferocious starburst, there would be little fuel left for future activity, and the massive stars born in that event would have lived fast, died young in supernova, and left behind remnants like neutron stars or black holes. The center would then appear quiet because it is, in a sense, recovering from its own past excess, in a dormant phase between major cosmic events. The most intriguing possibility of all brings us back to the missing black hole. An active galactic nucleus is only active if its central black hole is actively consuming matter. If the black hole is indeed absent, either ejected from the galaxy or lying completely dormant, then the brilliant engine of an AGN simply cannot exist. The silence would be a direct consequence of that emptiness. This would make the Pinwheel Galaxy a rare and invaluable example of a mature spiral that has lost its central engine, allowing astronomers to study how a galaxy evolves when that dominant gravitational anchor is suddenly removed. The unusual quiet isn't just an absence of noise, it's a clue. It tells a story of a galactic center that operates differently from any other we know, forcing us to reconsider the very conditions necessary for a galaxy to light up its core. Yet as we shift our gaze from the grand architecture of stars to the finer details of its raw material, we uncover another profound layer of the pinwheel's mystery, one written not in light but in the faint whisper of radio waves. The galaxy is enveloped in a massive, dynamic reservoir of neutral hydrogen gas, the primordial fuel for star formation. In a typical spiral galaxy, This gas should trace a perfect mirror image of the luminous spiral arms, concentrating in the dense regions where gravity pulls it together to eventually collapse into new stars. But in the Pinwheel Galaxy, the hydrogen tells a very different and far more chaotic story. Vast, looping bridges of gas stretch far beyond the optical disc, connecting regions that have no business being linked. Enormous, solitary clouds float in the galactic halo like phantom islands, unanchored to any visible structure. The distribution is clumpy, asymmetrical, and in many places completely divorced from the beautiful spiral arms we see in photographs. This bizarre disconnect is a glaring signpost pointing to a recent and violent gravitational disturbance. The most logical explanation is that the Pinwheel Galaxy has not been spinning in peaceful isolation. It has been interacting with its neighbors. The peculiar hydrogen structures act like cosmic fingerprints, preserving the evidence of a close encounter or even a direct collision with a smaller, passing galaxy. Imagine dragging a finger through a cloud of smoke. The swirling patterns and tendrils that form are a direct record of that motion. In the same way, the gravitational pull of a dwarf galaxy passing through or near the pinwheel's disk would have violently stirred its hydrogen reservoir, pulling immense streams of gas out into the halo and leaving behind these bizarre, filamentary bridges as a lasting testament to the encounter. Some of the orphan clouds we see could be the shredded remains of that smaller galaxy itself, its stars long since dispersed or dimmed, leaving only this gaseous ghost as evidence of its demise. However, not every astronomer is convinced a galactic interaction is the sole culprit. The sheer scale and specific morphology of some hydrogen features have prompted investigations into whether unknown physical processes could be at work within the gas itself. Could there be mechanisms of magnetic field interaction or types of hydrodynamic instabilities that we don't yet fully understand? Processes that can spontaneously structure gas on such colossal scales without requiring an external trigger. It's a tantalizing possibility, suggesting that our models for the behavior of interstellar matter, especially in environments as extreme as the outer reaches of a galaxy, might still be incomplete. The anomalous hydrogen map of the Pinwheel Galaxy is therefore more than just a puzzle. It's a diagnostic tool. By studying the motion and temperature of these gas clouds, scientists can effectively rewind the tape, calculating the precise timing and dynamics of the proposed interaction. They can measure how much gas was lost to intergalactic space forever and how much is falling back onto the disk, fueling future generations of stars. This chaotic distribution of hydrogen is not a static picture. It's a snapshot of a galaxy in recovery, slowly reorganizing itself after a cosmic upheaval, its future evolution written in the invisible flow of its most fundamental ingredient. Yet another layer of the pinwheel's mystery reveals itself not within its brilliant disk, but in the sparse celestial entourage that surrounds it. Most large spiral galaxies, including our own Milky Way, are attended by a majestic swarm of globular clusters, ancient, dense balls of hundreds of thousands of stars each, orbiting the galactic core like a cloud of ancient fireflies. These clusters are cosmic fossils nearly as old as the universe itself, and their number and distribution tell the story of a galaxy's earliest, most violent years of formation. For a galaxy of the pinwheel's immense size and majesty, astronomers expected to find a rich system of perhaps several hundred of these ancient relics. The reality is a profound shock. The Pinwheel Galaxy is surrounded by a pauper's share of globular clusters, a number so surprisingly low it forces a complete re-examination of the galaxy's entire history. This deficit is far more significant than a simple head count. It's a missing chapter in the galaxy's biography. The prevailing theory of galaxy formation, the hierarchical model, suggests that large galaxies like the Pinwheel were built over billions of years through the merger and assimilation of countless smaller protogalaxies. Each of these dwarf galaxies would have brought its own population of globular clusters into the merger. The process should have left the pinwheel with a vast and rich system of clusters, a visible record of its violent growth. The fact that it has so few indicates that this story may be incomplete, or that the pinwheel's history took a radically different path. Perhaps it formed more peacefully and in greater isolation than other spirals, avoiding the dramatic collisions that would have donated these stellar treasures. Alternatively, a cataclysmic event in its past might have wiped them out. This second possibility opens a dramatic and destructive line of inquiry. Globular clusters are incredibly resilient, but they are not indestructible. As they orbit the galactic center, they can pass through the dense galactic disk. The tremendous gravitational tidal forces during these passages can physically rip a cluster apart, stretching it out into a long stream of stars that eventually dissolves into the galaxy's general halo. If the Pinwheel Galaxy experienced a period where its disk was unusually dense or dynamically heated, it could have acted as a destruction zone, systematically shredding a once populous cluster system. We may be looking at the aftermath of a galactic-scale massacre, where only the hardiest or most strategically orbits clusters survived the purge. A third, and perhaps most intriguing, theory suggests the clusters weren't destroyed, they were never there to begin with. The initial conditions during the pinwheel's birth may have been uniquely unfavorable for globular cluster formation. These clusters require incredibly dense and massive clouds of gas to collapse and form thousands of stars at once in a tightly bound group. If the primordial gas that formed the pinwheel was too hot, too turbulent, or simply not dense enough in the right regions, that prolific cluster formation might have been stifled. The galaxy would have been born impoverished, destined to forever lack the ancient stellar jewelry that adorns its peers. Each of these scenarios paints a vastly different portrait of the pinwheel's evolution, from a violent history that erased its past to a surprisingly quiescent one that never allowed for a glorious beginning. Its missing clusters are a silent testament to a story we are only just beginning to hear. And just when we thought the Pinwheel Galaxy had shown us all its cards, it reveals a phenomenon that operates not in the slow, grand movements of stars and gas, but in sudden, brilliant, and fleeting flashes of high-energy light. Deep within its spiral arms, astronomers have detected what are known as ultra-luminous X-ray sources, or ULKs. These are not your typical cosmic emitters. They are beacons of X-ray radiation so intensely bright that they can, for a time, outshine the entire output of our Sun across every wavelength combined. What makes them truly mysterious and why they've earned the nickname phantom sources is their bizarre behavior. They flare up to incredible brightness without any warning, dominate the X-ray sky for weeks or months, and then they abruptly vanish, fading back into the background noise of the galaxy, often leaving no visible trace behind in optical telescopes. The natural explanation for such a powerful and compact energy source would be a stellar mass black hole, the remnant of a massive star greedily feeding on a companion star. As gas is ripped from the donor star and spirals down into the black hole's accretion disk, it heats up to millions of degrees, releasing this torrent of X-rays. But there's a fundamental problem. There is a theoretical maximum to how brightly such a system can shine, known as the Eddington limit. It's a point where the outward pressure of all that radiation actually overwhelms the inward pull of gravity, effectively blowing the cosmic dinner plate out of the black hole's hands and shutting down the feeding frenzy. These ULXs in the pinwheel are screaming past that limit, shining tens or even hundreds of times brighter than they should be able to. It's a physical impossibility according to our standard textbooks, which means something far more exotic must be powering these cosmic lighthouses. This has sent theorists scrambling for new explanations, each more fascinating than the last. One compelling idea is that we are not looking at standard stellar black holes, but at something entirely new, intermediate mass black holes. These would be the long-sought missing link between the stellar mass black holes formed from dying stars and the supermassive giants that anchor galaxies. An intermediate black hole with a mass of several thousand suns would have a much higher Eddington limit, allowing its feeding process to reach these incredible luminosities without tearing itself apart. Their formation is itself a mystery, potentially created in the dense core of a globular cluster or from the direct collapse of primordial gas in the early universe. Finding one would be a watershed moment in astronomy. Another radical possibility involves not a change in the black hole itself, but a change in how it feeds. Perhaps these phantom sources are not breaking the laws of physics, but are finding a clever loophole. If the accretion disk around the black hole is not a simple, symmetrical disk, but is instead warped or funneled like a cosmic tornado, the radiation could be beamed directly toward us. We would be looking straight down the barrel of this high-energy jet, receiving a concentrated dose of its brilliance while the actual total output of the system remains within physical limits. It would be an incredible illusion of power, a trick of cosmic geometry that makes a merely powerful object appear impossibly luminous from our specific vantage point. Then there's the most speculative yet thrilling theory of all, that some of these sources might not be black holes at all. Could they be signatures of entirely new classes of astrophysical objects, perhaps exotic stars made of dense quark matter or other theoretical constructs that we haven't even dreamed up yet? The phantom X-ray sources of the Pinwheel Galaxy stand as one of its most persistent and energizing puzzles. Each new flare-up is a potential clue, a brief window into the most extreme physical processes in the universe, challenging us to look deeper and rethink our understanding of how matter and energy behave under conditions we can scarcely imagine. While the phantom X-ray sources reveal hidden violence in brief, brilliant flashes, the Pinwheel Galaxy also holds evidence of eruptions operating on a far grander scale and timespan, written not in X-rays but in the silent, steady hum of radio waves. Giant radio telescopes have mapped the galaxy not by its visible starlight, but by its emission at these long wavelengths, and the resulting image is breathtakingly strange. Woven through and around the familiar spiral arms are colossal, faintly glowing loops and giant arcs of radio emission. These are not mere echoes of the star-forming regions we see. They are immense, independent structures, some stretching for thousands of light years, tracing patterns in the void that have no counterpart in the optical, infrared, or ultraviolet views of the galaxy. They are like ghostly, cosmic graffiti, spray painted across the heavens by an unseen hand. The existence of these radio loops points to powerful, large-scale phenomena that have shaped the galaxy's environment in ways we are only beginning to comprehend. The most plausible explanation involves the galaxy's magnetic field. We know that spiral galaxies are permeated by vast, invisible magnetic fields, often aligned with their spiral arms. But the intricate, looped structures seen in the pinwheel suggest a magnetic landscape of incredible complexity and strength, far more turbulent and organized than our standard models predict. Charged particles like electrons become trapped by these magnetic field lines, spiraling around them and emitting synchrotron radiation, the very radio waves we detect. The sheer size and brightness of these loops imply that the magnetic fields guiding the particles are exceptionally powerful and structured in coherent, giant shapes, like invisible tunnels sculpting the flow of energy through the galaxy. Another compelling theory reaches back into the galaxy's deep past, suggesting we are witnessing the fading aftermath of a cataclysm so immense it temporarily dwarfed the entire galaxy. These radio loops could be the remnant shells of ancient titanic outbursts from the galactic center, even if that center is now quiet. Billions of years ago, if the supermassive black hole was present and active, it could have launched jets of relativistic particles and energy at nearly the speed of light. These jets would have plowed through the galactic halo, inflating massive bubbles of energetic gas that expanded outward over eons. Even after the central engine shut down, the shells of these bubbles would persist, their constituent electrons still spiraling in weakened magnetic fields, continuing to emit radio waves as a permanent fossil record of that past fury. We would be seeing the ghost of a scream from the galaxy's youth, A third, more interactive possibility involves the pinwheel's place within its local group of galaxies. These radio structures might not be self-contained at all. They could be the result of the galaxy plowing through the tenuous intergalactic medium that exists between galaxies in a cluster. This process, called ram pressure, can compress magnetic fields and generate shock waves that accelerate particles and light up radio emission along the galaxy's leading edge. Alternatively, a close gravitational encounter with a neighbor could have stretched and amplified the galaxy's magnetic field on a massive scale, twisting it into the large, loop-like configurations we now observe. Each of these explanations, the magnetic, the historic, and the interactive, paints a picture of a dynamic system where energy is transferred and shaped across incomprehensible distances. These inexplicable radio loops are more than just pretty patterns. They are a direct window into the most powerful forces that govern a galaxy's evolution, forces that operate in the dark, sculpting the cosmos in ways we are only just learning to see. Moving inward from the halo's radio whispers and into the very core of the galaxy itself, we encounter a structural quirk that is both geometrically striking and deeply puzzling. When viewed in the infrared spectrum, a wavelength that pierces through obscuring dust to reveal the distribution of older stars, the central region of the Pinwheel Galaxy doesn't present the smooth, rounded, or bar-like bulge we see in most spirals. Instead, it resolves into a distinct and almost perfect diamond shape, a stark geometric form that stands in brilliant contrast to the graceful curves of its surrounding spiral arms. This isn't a minor anomaly in the data. It's a fundamental architectural feature that challenges our classic definitions of what a galactic core should look like. In a typical spiral galaxy, the central bulge is a dense, roughly spherical or slightly flattened swarm of mostly older, redder stars. It's thought to form through two primary mechanisms, either rapidly in the early universe through gravitational collapse or more slowly over time as the galaxy's bar structure funnels material inward. The pinwheel's crisp diamond shape fits neither of these models comfortably. Its defined angles and edges suggest a very different history, one potentially dominated by dynamic forces rather than quiet accretion. This peculiar structure immediately suggests that the core is not a calm, settled place, but a region that has been recently, or is still being, violently disturbed. One of the most compelling theories points directly to the gravitational influence of the galaxy's unseen dark companion. As this massive, dark galaxy continues its long dance around the pinwheel, its immense gravitational pull doesn't just affect the outer rotation, it can also torque and twist the very center of the visible galaxy. This gravitational perturbation could be literally pulling the core out of its natural spherical shape, stretching it into this distinct diamond-like form. It would be a continuous process, a slow, cosmic sculpting where the invisible hand of dark matter is actively molding the heart of a galaxy before our eyes. We may be witnessing a real-time demonstration of how dark matter halos can influence not just a galaxy's overall motion, but its most intimate internal structures. An equally fascinating possibility is that we are seeing the aftermath of an ancient head-on collision. If a smaller galaxy were to merge with the pinwheel on a direct radial trajectory, plunging almost straight into the core, the incredible gravitational shockwave could have fundamentally rearranged the orbits of the central stars. Instead of their random, buzzing hive orbits that create a rounded bulge, the stars could have been organized into more aligned, resonant orbits that, when viewed from our perspective, create the illusion of sharp edges and a diamond profile. This would make the core not a classic bulge at all, but a unique structure known as a pseudobulge, one built not by early collapse but by a specific and dramatic seismic event in the galaxy's history. The implications of this discovery reach far beyond simple classification. The shape of a galaxy's core is a direct tracer of its formation history and its underlying gravitational potential. The pinwheel's diamond core forces us to ask whether it ever had a classical bulge to begin with, which in turn questions the entire standard narrative of how this magnificent spiral was assembled. Its unique structure makes it a vital case study for astrophysicists running supercomputer simulations of galaxy formation. To recreate this diamond, the simulations must now account for a specific set of violent interactions and perturbations that were previously considered uncommon. This isn't just a strange shape, it's a key that could unlock a deeper understanding of the dynamic processes that shape all galaxies, revealing a universe where even the most fundamental structures can be forged in the chaos of collision and the relentless pull of the unseen. Now we arrive at a contradiction at the very core of the Pinwheel's life cycle, a puzzle that has astronomers questioning the galaxy's current age and vitality. On one hand, portions of the galaxy, particularly that overdeveloped spiral arm, blaze with the brilliant blue light of massive, young O and B-type stars and the telltale pink glow of vast hydrogen nebulae, the raw nurseries of stellar birth. This suggests a galaxy in its prime, furiously forging new generations of stars. Yet, when scientists attempt to quantify this activity by measuring the galaxy's overall star formation rate, other methods tell a very different story. The amount of ultraviolet light emitted, a direct indicator of recent star birth, seems oddly low for a galaxy of its size and gas richness. It's as if you walked into a factory that appears to be a hive of activity, with conveyor belts moving and machinery humming, but the output at the loading dock is surprisingly meager. This discrepancy is known as the star formation paradox, and it forces us to ask a fundamental question. Is the Pinwheel Galaxy a vibrant, young stellar factory, or is it quietly winding down? One explanation for this contradictory evidence lies in the galaxy's violent and disruptive history. That same gravitational encounter that lopsided its arms and stirred up its hydrogen gas may have also triggered a tremendously powerful but incredibly brief burst of star formation. Think of it like a wildfire that races through a dry forest. It burns intensely and consumes all the available fuel in a very short period, leaving behind ashes and a landscape that will take a long time to recover. The brilliant blue stars we see in that one dominant arm could be the last embers of that great fire, the final massive stars born from a gas supply that was mostly used up or scattered by the galactic collision. The galaxy is now in a period of relative quiescence, its overall star formation rate having plummeted after that single, extravagant event. We are simply witnessing the aftermath, where the visible signs of recent birth are spectacular but not representative of the current, much slower pace. Another compelling theory delves into the efficiency of the process itself. Star formation requires more than just vast amounts of gas. It requires that gas to be cold, dense, and unstable enough to collapse under its own gravity. It's possible that the interstellar environment within the pinwheel has become hostile to this process. The tremendous energy output from all those newly formed massive stars, their intense ultraviolet radiation, and the powerful shock waves from their eventual supernova explosions could be heating and dispersing the surrounding gas clouds. This feedback effect effectively shuts down further star formation by preventing the gas from cooling and condensing into new stellar seeds. The galaxy might be choking on its own success, its past productivity having created conditions that stifle its future growth. The raw fuel is still there, but it's been heated into a state where it simply cannot collapse. A more subtle possibility involves the initial distribution of that star-forming gas. The hierarchical model of galaxy formation suggests that gas falls into galaxies in clumps and streams. If the gas recently accreted by the pinwheel arrived in an unusually warm or diffuse state, rather than in cold, dense clouds, it would be inherently less efficient at forming stars. The total amount of raw material might be sufficient for vigorous activity, but its physical state dooms it to a languid pace. This would mean the paradox isn't about the rate at all, but about the quality of the fuel itself. The Pinwheel Galaxy could be rich in gas, yet poor in the specific kind of gas that leads to stars. Unraveling this mystery requires looking at the galaxy not as a single entity, but as a collection of individual neighborhoods, each with its own unique conditions. By mapping the temperatures, densities, and motions of the gas clouds themselves, astronomers hope to determine whether the pinwheel is a galaxy recovering from a feast, one struggling under its own feedback, or one simply waiting for the right kind of ingredients to arrive. But beyond the grand movements of stars and the ebb and flow of gas, some of the most profound mysteries of the Pinwheel Galaxy are written in the most delicate of scripts: its light. When astronomers pass that light through a spectrograph, splitting it into a rainbow of wavelengths to create a unique chemical fingerprint, they find lines and signals that simply do not belong. Scattered across this spectral barcode are faint, unidentified emission lines, tiny spikes of brightness at specific wavelengths that do not correspond to any known element or molecule. These aren't just minor curiosities, they are spectral anomalies that have stubbornly resisted identification despite decades of intense scrutiny, standing as ghostly signatures of physical processes we have yet to discover. This challenge is akin to a detective having a complete fingerprint from a crime scene, but finding no match for it in any database on Earth. Our current catalog of spectral lines is immense, built from over a century of laboratory experiments where we've excited every element and thousands of molecules to see the precise wavelengths of light they emit. When we point our telescopes at a cosmic object, we expect to see the familiar signatures of hydrogen, helium, oxygen, nitrogen, and carbon. In the pinwheel, we do see those. But we also see these other lines, these spectral interlopers, that hint at something new happening in the vast spaces between its stars. The very persistence of these lines, showing up consistently across different observations, confirms they are real features and not mere instrument glitches or noise. They are a genuine message from the galaxy that we have not yet learned how to read. The hunt for an explanation has led scientists down several fascinating and at times deeply theoretical paths. One of the most promising ideas involves complex carbon-based molecules known as polycyclic aromatic hydrocarbons, or PAH. These are essentially tiny, sooty particles, like the specks you might find in candle smoke, and they can fluoresce when bathed in ultraviolet light from nearby stars. While we have identified spectral features for many PAHs, it's entirely possible that more complex, exotic versions of these molecules, formed under the unique conditions within the pinwheel, could be producing emission at wavelengths we haven't yet measured in a lab here on Earth. The galaxy could, in effect, be a vast chemical factory, brewing organic compounds more complex than any we've ever seen. An even more exotic possibility points to the conditions of the interstellar medium itself. The space between stars is not a perfect vacuum, it's a diffuse plasma of charged particles. Under certain extreme conditions of density and temperature that are difficult to replicate on Earth, atoms can become excited in unusual ways, or electrons can transition between energy states in highly ionized atoms of familiar elements like iron or oxygen, but in a manner that produces a spectral line we simply don't recognize because we've never observed it in such a context. It's not that the element is unknown, it's that the physical state of that element is so extreme that its light signature becomes unfamiliar. Then there is the most thrilling, albeit least likely, hypothesis that these lines are the signature of an entirely unknown element. The periodic table as we know it is complete up to very high atomic numbers, but who is to say that under the immense pressures within a stellar core or during a supernova, or even in the strange environment around a neutron star, a stable, super-heavy element couldn't be briefly forged? Its spectral signature would be completely new to science. While this is a long shot, it illustrates the depth of the mystery. These unidentifiable lines are more than just data points. They are direct challenges to our understanding of chemistry and physics. They remind us that our knowledge, however advanced, is based on the conditions we can create and observe on our own tiny world. The Pinwheel Galaxy, with its different history, different composition, and different physical scale, might be operating under a set of rules we are only just beginning to glimpse. Each strange spike in its spectrum is an unanswered question, a quiet call from 21 million light-years away, urging us to look closer and dream bigger. And now we arrive at a cosmic paradox that reaches beyond the pinwheel itself, challenging our most fundamental understanding of gravity and mass. According to Einstein's theory of general relativity, a massive object like a galaxy should act as a gravitational lens. Its immense gravity ought to warp the very fabric of spacetime around it, bending and magnifying the light from even more distant galaxies located directly behind it from our point of view. This effect isn't just theoretical. We observe it throughout the universe, using it as a vital tool to weigh galaxies and even to map the distribution of dark matter. For a galaxy as colossal as the Pinwheel, with its unexpectedly massive dark matter halo, the lensing effect should be pronounced and easily measurable. Yet, when astronomers search for this telltale distortion, this cosmic magnifying glass, they find nothing. The region of space around the pinwheel is curiously, inexplicably flat. This absence is far more than a simple negative result. It's a direct conflict between two independent ways of measuring the galaxy's mass. The first method, using the motion of its stars and gas, tells us the pinwheel is incredibly heavy, with a vast amount of unseen matter tugging on everything. The second method, relying on the bedrock principles of general relativity, suggests there is simply not enough mass present in the right place to warp light. It's as if two different scientific scales, both trusted and proven, are giving us completely different weights for the same object. This discrepancy forces us to confront a handful of deeply profound possibilities, each with staggering implications. The first and most conservative explanation is that the dark matter halo, while massive, is configured in a way that makes it a terribly inefficient lens. Gravitational lensing is most effective when mass is concentrated. A compact, dense halo would warp spacetime dramatically, but a vast, incredibly diffuse and fluffy halo might not. If the pinwheel's dark matter is spread out over an unexpectedly enormous volume, its gravitational field would be weaker at any given point, resulting in a gentler, undetectable curvature of spacetime. We would be looking at a ghost that has a tremendous total weight but casts only a very faint, blurry shadow. A much more radical idea is that our understanding of gravity itself is incomplete. The rules laid out by Einstein's theories have passed every test thrown at them for over a century, but they are ultimately a model of the universe. What if, on the immense scales of a galactic halo, gravity behaves differently than we predict? Modified Newtonian dynamics, or MUND, is a proposed alternative that suggests we don't need dark matter at all. Instead, gravity simply operates with a different set of rules at low accelerations, like those found in the outer reaches of galaxies. The pinwheel's lack of lensing could be a key data point in favor of such a theory, indicating that the apparent extra mass we infer from star motions is an illusion created by our flawed gravitational equations. There is a third, equally fascinating possibility that the lensing is happening, but we are missing it because we are looking at the wrong thing. Perhaps the lensed images of the background galaxies are so faint or so perfectly aligned with the foreground light of the pinwheel itself that our current telescopes and processing techniques cannot tease them apart from the noise. The galaxy's sprawling, face-on orientation and its intense regions of star formation create a brilliant and complex backdrop that could easily be hiding subtle gravitational arcs. Future observatories, with their superior resolution and sensitivity, might finally peel back this luminous veil to reveal the lensing that has thus far remained hidden. Until then, the silent space around the Pinwheel Galaxy stands as one of its most compelling mysteries, a quiet challenge to our core assumptions about the nature of gravity, mass, and the invisible fabric of the cosmos. But perhaps one of the most visually counterintuitive mysteries of the Pinwheel Galaxy involves the very motion of its building blocks. While the vast majority of the galaxy's stars, gas, and dust all rotate in a single, coherent direction, the majestic spin that defines its spiral arms, astronomers have made a deeply strange discovery. Nestled within this grand flow are entire clouds of hydrogen gas that are moving in the exact opposite direction, like salmon swimming upstream against a powerful cosmic current. These counter-rotating clouds present a glaring violation of the standard model of galactic evolution, which assumes a relatively ordered and unified rotation from a shared origin. Their existence is a clear sign that the pinwheel's history is far more complex and violent than its beautiful, placid appearance suggests. The most immediate and compelling explanation for this backward motion is that this gas is not native to the pinwheel at all. It is an invader, a captured resource. Throughout its long life, the galaxy has likely cannibalized smaller dwarf galaxies that ventured too close. It's also continuously moving through the cosmic web, sweeping up the faint filaments of primordial gas that stretch between galaxies. If this incoming material approaches from a certain angle, it can be assimilated with a rotational direction that is completely opposite to the galaxy's established spin. Imagine a new rider jumping onto a spinning merry-go-round but running in the opposite direction. They've joined the structure, but their motion is completely at odds with its rotation. The presence of these counter-rotating clouds could therefore be the lingering signature of a recent cosmic meal, the last bits of a devoured dwarf galaxy that haven't yet been slowed down and integrated into the galaxy's dominant rotation. However, not every astronomer is convinced the answer lies entirely outside the galaxy. An alternative and equally fascinating theory suggests that the explanation might be found in the incredibly complex internal dynamics of the pinwheel itself. The galaxy is not a solid body. It's a fluid-like disk of gas and stars where waves of density can travel, and massive spiral arms can create powerful gravitational wakes. It's possible that interactions between these spiral arms and the surrounding gas could, under specific conditions, create regions of such intense turbulence and shear that they effectively slingshot pockets of gas into a retrograde orbit. This would be an internal recycling process, a testament to the sheer energetic power contained within the galaxy's structure, capable of flinging its own material into bizarre and unexpected trajectories without any external help at all. Pinpointing the true origin of these rebellious clouds is a delicate forensic task. By carefully measuring not just their direction, but also their velocity and chemical composition, scientists can gather crucial clues. Gas that originated in a dwarf galaxy will often have a different metallicity, a lower abundance of heavy elements forged in previous generations of stars compared to the pinwheel's own enriched gas. If the counter-rotating clouds show this primordial signature, it would be strong evidence for the accretion theory. Furthermore, if their orbits are still highly eccentric and unrelaxed, it would indicate a very recent capture, perhaps within the last few 100 million years. These clouds are more than just anomalies. They are celestial timestamps, recording the last major event that shook this galaxy and forever altered its composition. Their contradictory motion is a permanent testament to the fact that galaxies are not isolated island universes, but dynamic entities, constantly growing and changing through violent encounters and the ongoing acquisition of foreign matter from the vast intergalactic sea. This apparent solitude is another stark puzzle. According to our most successful cosmological model, a galaxy the size of the pinwheel shouldn't be an island. It should be the radiant center of its own bustling local group, the gravitational anchor for a veritable swarm of dozens, if not hundreds, of smaller dwarf satellite galaxies. These tiny galactic companions are considered the fundamental building blocks of the universe, the leftover scraps from which massive galaxies like the pinwheel were assembled over billions of years. Their predictable abundance is a cornerstone of our understanding of dark matter and cosmic structure. And yet, when we census the immediate cosmic neighborhood around the pinwheel, the result is a profound and surprising emptiness. The expected rich population of satellite galaxies is conspicuously, bafflingly absent. This missing entourage forces astronomers to consider three dramatic possibilities, each with far-reaching implications. The first is a history of unparalleled cosmic violence. It's possible the pinwheel did indeed have a full suite of satellite galaxies, but it was an exceptionally ruthless predator. Through a series of close gravitational encounters over its long life, it may have completely cannibalized and destroyed every single one of these smaller companions, tearing them apart and assimilating their stars and gas into its own majestic spiral arms. The lopsided structure and the strange hydrogen streams we discussed earlier could be the lingering evidence of this galactic feast. In this scenario, the pinwheel stands as a solitary monarch in a kingdom it completely consumed. A second, and perhaps more unsettling, theory challenges the model itself. It suggests the satellites weren't destroyed, they simply never formed to begin with. The conditions in this particular region of the universe during the earliest epochs after the Big Bang might have been uniquely unfavorable for the birth of small dark matter halos, the gravitational seeds necessary for dwarf galaxies to coalesce. Perhaps the primordial density fluctuations here were too smooth, leaving no small-scale clumps for gas to collect around. If this is true, then the Pinwheel Galaxy may have formed in a cosmic void, a rare giant that grew in exceptional isolation, forever lacking the entourage that theory says it must have. This would require a significant tweak to our models of how structure forms in the universe, suggesting the process is less uniform than we currently believe. The third possibility is a game of cosmic hide and seek. It's plausible that the satellite galaxies are there, but we simply cannot see them. They could be composed almost entirely of dark matter, with so few stars that they emit virtually no light, making them invisible to our current optical surveys. We've already discussed the evidence for one massive dark companion. Could there be an entire population of these invisible dwarfs, a shadowy court orbiting the luminous pinwheel? Their presence would only be betrayed by their subtle gravitational influence, a tiny wobble in the motion of the outer disk or a microlensing event as they pass in front of more distant stars. Finding them would require incredibly precise measurements and a bit of luck. Unraveling this mystery is critical because these missing satellites are not just decorative, they are vital diagnostic tools. Their number, distribution, and orbital motions are a direct probe of the properties of the dark matter halo itself. A rich population of satellites would indicate a dense, clumpy halo, exactly as predicted by the cold dark matter model. Their absence, however, suggests a halo that is smoother and less structured, which could point toward more exotic types of dark matter particles that move faster and resist clumping on small scales. The quiet void around the Pinwheel Galaxy is therefore more than just an empty space. It's a profound question mark hanging over our entire understanding of how the cosmos builds its largest structures and what the mysterious dark matter that governs them is truly made of. Yet the mysteries of the Pinwheel Galaxy's influence extend beyond the gravitational and into the realm of pure light, revealing an ethereal structure that challenges our understanding of its very boundaries. In visible light, we see a magnificent spiral disk, but when we switch our view to the ultraviolet spectrum, the galaxy transforms into something entirely different. It is encased in a massive, faintly glowing halo of ultraviolet light that stretches tens of thousands of light years beyond the edges of its star-filled arms. This is not a sharp, defined edge, but a soft, colossal glow, a cosmic aurora that envelops the entire galaxy in a veil of high-energy photons. It's as if the galaxy is breathing out a luminous mist, a signature of processes occurring far from the bustling stellar nurseries of the main disk. This immense ultraviolet halo presents a fascinating puzzle because this type of light doesn't just appear on its own. Ultraviolet radiation is primarily the signature of very hot, young, and massive stars or of extremely energetic events. Finding it concentrated in the galaxy's sparsely populated outer halo, far from the dense gas clouds required to form new stars, is deeply counterintuitive. It forces us to ask where this energy is coming from and what physical mechanisms could possibly be at work in the galactic hinterlands to produce it. The most straightforward explanation points to a stellar exodus. The same violent gravitational interactions that distorted the galaxy's shape and sent hydrogen gas streaming into the halo could also have violently flung massive, young stars out there as well. These runaway stars, hurled from their birthplaces in the spiral arms, would continue to burn hot and bright during their short lives, their intense UV output lighting up the vast emptiness around them like lonely lighthouses in a dark sea. But there's another, more continuous process that could be at work: galactic feedback on a monumental scale. The combined effect of thousands of supernova explosions and the fierce stellar winds from massive stars in the disk creates a powerful, ongoing outflow. This wind, a hurricane of hot gas and charged particles, blows outward from the galaxy's plane, carrying energy and heavy elements into the halo. As this material travels outward and collides with the cooler, more stationary halo gas, it can create shock waves that heat the gas to extreme temperatures, causing it to glow in the ultraviolet. In this scenario, the UV halo is not made of stars, but is instead a gigantic and permanent shock front, the visible boundary of the galaxy's energy output impacting its own quiet exterior. A third and more speculative idea involves the galaxy's magnetic field once again. If magnetic field lines are stretched from the disk far out into the halo, they can act like highways for high-energy electrons. These charged particles, accelerated by supernova or other violent events, could travel along these lines and then release their energy as synchrotron radiation, which can include ultraviolet wavelengths as they spiral around the magnetic fields in the halo. This would make the glow not a thermal phenomenon from hot gas, but a non-thermal one from frenetic particles, painting the halo with light born from magnetic chaos. Determining the true cause requires peeling apart the light itself, analyzing its exact spectrum to see if it matches the signature of hot stars, heated gas, or synchrotron radiation. Each answer tells a different story about the pinwheel's life cycle, revealing whether its outer reaches are a graveyard for exiled stars, a constant energy front, or a realm ruled by invisible magnetic forces. This beautiful, enigmatic glow is a direct measure of the galaxy's power to shape not only its own disk, but the vast, empty space that surrounds it. But now we descend from the vast, energetic halo and into the very hearts of the stellar nurseries themselves, to the colossal clouds of gas and dust where stars are born. Here, within the Pinwheel Galaxy's spiral arms, we find another profound divergence from our cosmic neighborhood. The giant molecular clouds in M101, the fundamental cradles of star birth, are not behaving like those we've studied in our own Milky Way. They possess a strange and unfamiliar set of physical properties: unusual densities, unexpected temperatures, and star formation efficiencies that defy the established rules of interstellar chemistry and physics. It appears the very recipe for building stars is different in this distant pinwheel. In our galaxy, we've grown accustomed to a certain rhythm. A giant molecular cloud will slowly coalesce, eventually reaching a tipping point where pockets within it begin to collapse under their own gravity, igniting new stars. There's a generally predictable relationship between the mass of the cloud, its density, and how many stars it will ultimately produce. But the clouds in the Pinwheel Galaxy seem to be operating on a different schedule entirely. Some exhibit densities far higher than anything found locally, yet they are curiously inert, hoarding their immense mass without giving birth to stellar clusters. It's like finding forests of incredibly dense, dry timber that simply refuse to catch fire. Conversely, other clouds, which by all accounts should be too diffuse and cold to be productive, are instead blazing with unexpected stellar activity, forming stars at a rate that seems to come out of nowhere. This strange inefficiency and unpredictability point to a powerful external influence shaping the conditions within these nurseries. The leading theory once again points to the galaxy's violent and lopsided history. The same gravitational shockwaves that distorted the galaxy's arms and flung gas into the halo would have also sent powerful compression waves racing through the interstellar medium. These waves could have violently squeezed certain clouds to unusually high densities in a very short time, but perhaps they were compressed so rapidly that the cloud hasn't yet had time to fully adjust and begin the slow process of collapse. They are frozen in a state of potential, waiting for the next trigger. Meanwhile, other clouds may have been sheared apart or had their internal dynamics so thoroughly disrupted that their ability to form stars was permanently damaged. Yet the answer may not lie solely in gravity. The chemical composition of these clouds could be fundamentally different. Star formation is a delicate dance between gravity pulling inward and gas pressure pushing outward. This pressure is heavily influenced by the cloud's chemistry, specifically the presence of complex molecules like carbon monoxide that help the gas cool and condense. If the Pinwheel's clouds have a different mix of elements, or if they are enriched with unexpected types of dust grains from many generations of supernova, their cooling efficiency could be dramatically altered. A cloud that cannot cool effectively cannot collapse, no matter how massive it is. The Pinwheel might be showing us that the journey from a cold cloud to a blazing star is far more sensitive to chemical recipe than we ever imagined, and that recipe can vary significantly from one galaxy to the next. Furthermore, the ambient environment in the Pinwheel's disk is likely far more intense than in our own. The galaxy's high rate of star formation in its prominent arm means there is a constant barrage of ultraviolet radiation and powerful stellar winds pouring out from nearby young star clusters. This radiation can photodissociate molecules, breaking them apart and heating the cloud's outer layers, effectively sterilizing it and preventing star formation from propagating inward. In this scenario, a molecular cloud in the Pinwheel has to fight for its life against a much more hostile galactic environment, and its ability to form stars depends on whether its gravitational pull can win that fight against external pressure. These anomalous clouds are not just curiosities, they are the key to understanding why galaxies can have such different personalities. By studying why star formation is so capricious in M101, we are ultimately learning that there is no single, universal path to building stars. The process is deeply contextual, shaped by a galaxy's entire history, its chemical evolution, and the constant tumult of its dynamic environment. And just when we thought we had seen the full spectrum of the Pinwheel's strangeness, we encounter a phenomenon that unfolds not over eons, but within a human lifetime, challenging our perception of cosmic timescales. Scattered throughout its spiral arms are specific nebulae, those luminous clouds of gas and dust that refuse to behave as the permanent, slowly changing sculptures we expect them to be. Instead, they are time variable, showing measurable changes in their brightness and even their physical structure over periods as short as years or decades. This isn't a subtle shift, it's a rapid metamorphosis, suggesting that the processes shaping these stellar nurseries are far more dynamic and violent than our traditional models account for. The most immediate explanation for these flickering clouds points to a hidden puppet master, a variable central star. Many nebulae are emission nebulae, meaning they don't generate their own light but instead glow by reflecting or re-emitting the intense ultraviolet radiation from massive, hot stars embedded within them. If that central star itself is variable, perhaps a massive star undergoing violent eruptions or a binary system where one star periodically eclipses the other, the amount of energy pumping into the nebula would fluctuate dramatically. The nebula would effectively act as a giant amplifier, its entire structure dimming and brightening in response to the changing light from its hidden engine. We could be witnessing the final, dramatic throes of a massive star's life, as it ejects shells of material and experiences instabilities that cause its luminosity to surge and wane, casting an ever-changing light upon its own expanding cradle of gas. However, the changes aren't always uniform across the entire nebula. In some cases, specific filaments or knots within the cloud brighten or fade independently, or new structures seem to materialize where there was only empty space before. This points to a more complex and localized cause. It's possible we are seeing the real-time effects of shockwaves. A supernova explosion occurring nearby, even light years away, would send a powerful wave of energy and compressed matter racing through the interstellar medium at a significant fraction of the light speed. When this shock front slams into a dormant cloud of gas, it would violently compress the material, heating it instantaneously and causing it to light up with a sudden, brilliant glow that then slowly fades as the energy dissipates. We are essentially seeing the echo of a distant cataclysm, a ripple in the cosmic pond that temporarily illuminates everything it touches. Perhaps the most fascinating possibility is that we are witnessing the actual process of star formation itself, but in an incredibly accelerated and violent form. The prevailing theory suggests it takes millions of years for a dense core within a molecular cloud to collapse and ignite a new star. But what if, under certain extreme conditions, the process can happen much faster? The intense gravitational tides and pressure from the pinwheel's lopsided structure could be triggering a form of rapid and chaotic star birth. We might be seeing pockets of gas undergoing what's known as induced collapse, where the formation of one massive star nearby sends out shocks that trigger the collapse of another cloud core in a stellar domino effect. The changing brightness of the nebula could be the literal flickering on of new stars, one after another, their ignition flooding the surrounding gas with light, and then their powerful stellar winds blowing that same gas away to reveal the newborn star within. Monitoring these variable nebulae is like watching a time-lapse of the universe's most creative and destructive forces at work, offering us a front-row seat to the dramatic and fleeting moments that define the life and death of stars. Beyond the visible light and radio waves, another invisible force weaves through the Pinwheel Galaxy, one that has left astronomers utterly perplexed: its magnetic field. We often picture a galaxy's magnetic field as a smooth, elegant spiral, neatly aligned with its arms, guiding cosmic rays and gently influencing the flow of gas. But when scientists mapped the magnetic field of M101 using the subtle polarization of its radio emissions, they discovered a scene of pure chaos. Instead of a unified, organized pattern, the field is a turbulent tapestry of disorder. It reverses direction abruptly and unpredictably, creating a patchwork of magnetic domains that clash and tangle with no apparent rhyme or reason, completely divorced from the galaxy's beautiful spiral architecture. This magnetic anarchy is a profound puzzle because magnetic fields are not supposed to behave this way. In a typical spiral galaxy, the orderly rotation of the disk is thought to stretch and amplify the magnetic field, winding it up into a coherent spiral pattern that mirrors the arms, a process known as the galactic dynamo. The field in the Pinwheel Galaxy looks nothing like this. It appears shattered, as if some immense force has taken a hammer to it, scrambling its polarity into a confused jigsaw puzzle. This suggests that the standard dynamo theory, which works so well for other spirals, is either incomplete or has been completely overwhelmed here by a more powerful and disruptive influence. The prime suspect for this disruption is once again the galaxy's violent history. That same gravitational encounter that lopsided its arms and stirred its hydrogen gas would have sent powerful shockwaves rippling through the entire disk. These shocks would not only compress gas but also violently distort and tangle the magnetic field lines, essentially shredding the organized pattern into the fragmented mess we observe today. It's possible we are witnessing a magnetic field that is still in the process of recovering from a traumatic event, slowly trying to reorganize itself against the lingering turbulence. The dynamo is trying to rebuild order, but the aftermath of the chaos is still too great. Another compelling theory delves into the heart of star formation itself. The pinwheel's intense bursts of stellar birth, particularly in that one dominant arm, are factories of energetic feedback. Each massive star that forms and each supernova that explodes acts like a magnetic hand grenade. These events flood their local environment with hot gas and powerful winds that can locally dominate and even overpower the galaxy's large-scale magnetic field, carving out little bubbles of magnetic chaos with their own distinct polarity. With so much frantic activity happening across the disk, these individual bubbles of magnetic rebellion could be preventing the global field from ever settling into a stable, organized state. The galaxy's magnetic field may be a victim of its own stellar productivity, locked in a constant battle between the large-scale dynamo and 1,000 smaller, violent insurrections. The most exotic possibility involves the nature of the magnetic field's origins. Perhaps the field we see today isn't a product of the current dynamo at all, but a primordial relic. This theory suggests the magnetic field was frozen into the primordial gas that collapsed to form the Pinwheel Galaxy billions of years ago. If that initial field was itself tangled and complex, and if the galaxy formed quickly without a long period of smooth rotation to comb it out into order, that ancient disorder could have been preserved and simply amplified over time. We would be looking at a fossilized magnetic snapshot from the universe's infancy, a ghost from a time before the galaxy even took its current shape. Unraveling this magnetic mystery is about more than just mapping lines of force. It's a direct window into the most energetic processes shaping the galaxy. The magnetic field influences how cosmic rays travel, how gas clouds collapse to form stars, and how energy is transported throughout the disk. Its chaotic state in the pinwheel tells us that this galaxy is a place of immense and ongoing dynamic violence, where the fundamental forces that structure the cosmos are locked in a struggle that has, for now, produced a magnificent and bewildering confusion. And just as we witness the chaotic dance of magnetism within the disk, we find evidence of an even more violent process. The galaxy is actively ejecting its own lifeblood into the void. From the star-forming arms of the pinwheel, astronomers have detected massive, high-velocity outflows of gas colossal rivers of material being hurled outward from the galactic disk at speeds of thousands of kilometers per second. These are not gentle breezes, they are hurricane-force gales on a cosmic scale, powerful enough to physically strip a galaxy of the raw material needed to form future generations of stars. The sheer energy required to launch such immense quantities of gas against the relentless pull of the galaxy's own gravity is almost incomprehensible, and according to our best models, it simply shouldn't be happening on this scale. The most logical engine for such a powerful expulsion would be the combined fury of countless supernova explosions. In regions of intense star formation, massive stars live fast and die young, culminating in violent supernova that blast their outer layers into space. Individually, a supernova is a tremendous event, but collectively, they can create a superwind, a coordinated outflow where the combined shockwaves and energy from many explosions overwhelm the local gravity and punch a hole through the galactic disk, venting hot gas and heavy elements into the halo. The brilliant, star-filled arm of the pinwheel seems a perfect candidate for this kind of energetic feedback loop, where the very process of creating stars also sows the seeds for quenching future star formation by violently expelling the necessary fuel. However, when scientists calculate the energy observed in these outflows, a troubling discrepancy emerges. The numbers don't quite add up. The kinetic energy measured in these raging rivers of gas appears to exceed what should be possible, even from the most generous estimates of the supernova activity within the galaxy. This energy surplus points to the potential involvement of a more centralized and powerful engine, forcing us to once again confront the mystery of the galaxy's silent core. Could it be that the missing supermassive black hole isn't entirely dormant? Perhaps it is in a rare state of low-level activity, not consuming enough material to light up as a brilliant quasar, but still generating powerful jets of energy that travel outward and help to drive these massive outflows from within. These jets could be acting as an invisible piston, providing the extra push needed to explain the astonishing velocities we observe. Another, more exotic possibility involves the unique structure of the pinwheel itself. The galaxy's lopsided nature and its potential interaction with a dark matter companion might have created conditions ripe for a phenomenon known as a nuclear starburst wind. If a past gravitational encounter funneled a tremendous amount of gas directly into the galactic center in a short period, it could have triggered a brief but incredibly intense burst of star formation right around the core. The combined energy from the supernova in this compact central cluster would have been focused, channeled, and amplified, launching a far more powerful and concentrated outflow than what could be generated in the more spread-out spiral arms. We may be witnessing the lingering aftermath of this central firestorm, a wind that started with a concentrated bang and has since continued to blow. These high-velocity outflows are far more than a spectacular sight. They are a critical part of the galactic life cycle. By violently ejecting enriched gas, heavy elements forged in the hearts of stars and scattered in their depths, the Pinwheel Galaxy is seeding the intergalactic medium with the building blocks of planets and life. This process, known as galactic feedback, is what allows the chemical evolution of the entire universe to continue. Yet, the excessive energy of the pinwheel's outflows suggests this feedback might be operating in an overdrive mode we don't fully understand. This forces us to reconsider the balance of power within galaxies, hinting that the forces which govern their growth and eventual decline might be far more violent and efficient than we ever dreamed. Yet another profound gap in our understanding of the Pinwheel Galaxy lies not in what we see, but in what we fully expected to find and yet remains mysteriously absent. While the hunt for its central supermassive black hole continues, astronomers are also searching for a different class of cosmic predator, intermediate mass black holes. These are the crucial missing link in the black hole family, the elusive middle children with masses ranging from a few hundred to a few 100,000 times that of our Sun. They are theorized to be the building blocks that merge to form the supermassive black holes at the centers of galaxies, and the most likely places to find them are in the dense cores of globular clusters and within the violent hearts of the youngest star clusters. The Pinwheel Galaxy, with its rich population of both ancient globulars and brilliant new star-forming regions, should be a premier hunting ground for these objects. Yet, despite exhaustive searches, the galaxy has yielded precisely 0 confirmed detections. This absence is a deep cosmic silence that contradicts findings in other, similar spiral galaxies and directly challenges our theories of how black holes form and grow. Within the dense, ancient ball of stars that is a globular cluster, the conditions are perfect for the formation of an intermediate mass black hole. The frequent gravitational interactions and mergers of massive stars over billions of years should, according to many models, inevitably seed a black hole that slowly grows by consuming its stellar neighbors. In other galaxies, we find compelling evidence for this. We see stars orbiting an unseen, massive object at the center of a cluster, or detect the telltale X-ray flare of a black hole actively feeding. In the pinwheel's clusters, we find nothing but stars. The motions within their cores show no sign of a central, dark anchor of the expected mass. It's as if a fundamental law of cosmic demographics has been suspended here. The stepping stones between stellar and supermassive black holes are simply missing. The puzzle only deepens when we look to the galaxy's spectacular star-forming regions. These stellar nurseries are where the most massive stars are born and where the most massive stars die. When such a star collapses, it should leave behind a stellar mass black hole. In these incredibly dense environments, these black holes should sink to the center of the young cluster through a process called dynamical friction, eventually merging and building up an intermediate mass black hole. Again, the pinwheel defies this prediction. The brilliant, chaotic nebulas like NGC 5467 show no evidence of having forged a larger black hole at their core. The energy output, the motions of the gas, the behavior of the stars, all of it points to a system that, for some reason, has not followed the expected script of hierarchical growth. This glaring absence forces us to reconsider the very life cycle of these dense stellar environments. One possibility is that the pinwheel's clusters are fundamentally different. Perhaps their dynamics are more violent, and the process of building a central black hole is less efficient. When a large black hole does begin to form, the tremendous kick from a merger or a supernova might be ejecting it from the cluster entirely before it can grow to a significant size. The galaxy could be littered with these rogue, intermediate mass black holes drifting unseen in the dark spaces between the stars, having been violently expelled from their birth clusters and thus evading our detection. Another, more radical idea is that the initial conditions in the pinwheel simply didn't allow for their creation. The models that predict their formation rely on specific assumptions about the mass and density of the original star-forming clouds. If those clouds in the pinwheel had a different structure, perhaps they were less dense or more quickly disrupted by external forces. The process of runaway stellar mergers that creates an intermediate mass black hole might never get started. The clusters would form and evolve without ever creating a gravitational monster at their heart. The most profound implication of this absence touches on the entire story of how supermassive black holes came to be. If intermediate mass black holes are indeed the seeds from which the galactic giants grow, then a galaxy lacking them presents a monumental puzzle. How did the pinwheel's central black hole, if it ever existed, form and grow without these building blocks? It suggests that there might be multiple pathways to forming a supermassive black hole, and the Pinwheel Galaxy may have taken a road less traveled, one that bypassed this intermediate stage entirely. Its empty clusters are not just a local oddity, they are a direct challenge to a key chapter in our theory of cosmic structure, forcing us to acknowledge that the universe may have more than one recipe for creating its most enigmatic objects. And now we come to a mystery that strikes at the very heart of how we measure the cosmos, a flaw in one of astronomy's most trusted tools. For over a century, Cepheid variable stars have been our celestial yardsticks. These pulsating giants rhythmically brighten and dim over periods ranging from days to months, and there's a beautifully tight, predictable relationship between the period of their pulsation and their true, intrinsic brightness. By measuring how long it takes a Cepheid to cycle and comparing its true brightness to how dim it appears from Earth, astronomers can calculate its distance with remarkable precision. This period luminosity relationship is the bedrock upon which we've built our modern cosmic distance scale, allowing us to measure the vast expanses between galaxies. But within the Pinwheel Galaxy, this bedrock is showing cracks. A significant number of its Cepheid variables are not following the rules. Their pulsation periods and their actual brightness are out of sync, creating a troubling and pervasive uncertainty in our measurements of this crucial galactic neighbor. This deviation is far more than a minor calibration issue. It's a potential crisis in methodology. When we point our most powerful telescopes like Hubble and Webb at the Pinwheel Galaxy, we rely on these Cepheid variables to tell us with confidence that it is 21 million light-years away. But if the Cepheids themselves are lying, or more accurately, if they are behaving in a way we don't understand, then that foundational distance and every calculation that stems from it, like the galaxy's true size and luminosity, is thrown into question. The entire edifice of extragalactic astronomy depends on cross-checking different distance indicators, with Cepheids as the first crucial rung on the cosmic distance ladder. If that first rung is wobbly here, it casts a shadow of doubt on our understanding of the entire local universe. So what could cause these reliable standard candles to flicker so unpredictably? Astronomers are investigating several compelling and interrelated possibilities. The first and most straightforward explanation is metallicity, the abundance of elements heavier than hydrogen and helium within the stars. A star's metal content significantly influences its opacity and internal physics, which in turn governs how it pulsates. Cepheids in the Pinwheel Galaxy may have a different chemical composition than those we've used to calibrate the period-luminosity relationship in our own Milky Way. If the pinwheel's interstellar medium is richer or poorer in these heavy elements, its stars would form from different material, potentially altering their internal workings and causing them to deviate from the standard relationship we take for granted. We might be trying to use a ruler made for one type of metal to measure a star made of another. Another fascinating theory delves into the environments these stars inhabit. The Cepheids in the pinwheel aren't floating in isolation. They are embedded within the galaxy's intense spiral arms, regions bustling with turbulent gas, thick dust, and fierce radiation from neighboring young stars. This extreme environment could be physically affecting the stars themselves. Perhaps the powerful gravitational tides from the galaxy's lopsided mass distribution are subtly influencing the pulsation mechanisms. Or maybe the thick dust is not just dimming the starlight in a simple way that we can correct for, but is doing so unevenly across different wavelengths, fooling our instruments and making the stars appear anomalously bright or faint in ways that corrupt the clean period luminosity correlation. The most intriguing possibility, however, is that we are seeing the limits of our own astrophysical models. Our understanding of stellar interiors, while advanced, is still just a model. The precise physics that drives the pulsations in these giant stars involves complex processes of ionization and energy transport deep within their envelopes. The anomalous Cepheids in the pinwheel could be revealing a subtlety in this physics that we have not yet accounted for, perhaps related to their mass, age, or evolutionary stage. These rebellious stars are not broken. They are teaching us that the category of Cepheid variable might be broader and more diverse than we thought, containing subclasses with their own slightly different rules. By studying these outliers, we aren't just fixing a measurement error. We are being given a masterclass in stellar astrophysics, forced to refine our models and deepen our understanding of how these magnificent, pulsating giants truly work. Their refusal to conform is not a nuisance, but an invitation to learn. Yet another layer of the pinwheel's mystery reveals itself not in visible starlight or radio waves, but in the most energetic form of radiation the universe can produce. Throughout the galaxy's sprawling disk, astronomers have detected a faint, diffuse, and utterly persistent glow of gamma rays. This isn't the brilliant, localized flash of a collapsing star or the precise lighthouse beam of a spinning pulsar. It's a soft, omnipresent haze of high-energy photons that blankets the entire galactic structure. This persistent gamma-ray background is a profound puzzle because its distribution doesn't match up with any of the known factories for such extreme energy. We are left with a simple, haunting question. If this immense energy isn't coming from the usual suspects, what incredible physical processes are we missing? The most common sources for galactic gamma rays are the violent endpoints of stellar evolution. Supernova remnants, for instance, are famous for acting as natural particle accelerators. Their expanding shock waves can boost protons and electrons to nearly the speed of light, and when these relativistic particles collide with slower-moving gas atoms, they release their immense kinetic energy as gamma rays. Pulsars, the ultra-dense, rapidly spinning cores of dead stars, can also generate powerful gamma-ray beams from their magnetic poles. The problem in the Pinwheel Galaxy is that when researchers census all of these known objects and add up their expected contributions, the total falls dramatically short of the observed all-pervading glow. There is a massive excess of energy with no identifiable source, an entire population of ghostly accelerators operating in plain sight. This discrepancy has forced astrophysicists to consider the possibility of entirely new particle acceleration mechanisms at work. One compelling theory points to the galaxy's chaotic and powerful magnetic field. The tangled, turbulent state of the magnetism throughout the disk could be creating a perfect environment for a process called stochastic acceleration. Imagine the interstellar medium not as a calm pool of gas, but as a raging ocean during a storm. Particles could be caught in these chaotic magnetic waves, bouncing randomly from one region to another and gaining a little bit of energy with each collision. Over time, this could slowly but steadily build up a vast reservoir of high-energy particles throughout the entire galaxy, which would then uniformly illuminate the gas in gamma rays as they travel. It would be a democratic, galaxy-wide acceleration process rather than one confined to a few powerful but discrete engines. Another fascinating possibility involves the collective power of stellar winds. The Pinwheel Galaxy is a hotbed of massive star formation, and each of these giant stars blows off a powerful wind of charged particles. Individually, a stellar wind is not strong enough to produce significant gamma rays. But collectively, in the crowded environments of the galaxy's giant star clusters, these winds could collide and interact, creating massive shock fronts and turbulent regions where particles are accelerated to tremendous speeds. The combined output from thousands of these colliding wind systems spread across the spiral arms could be the source of the persistent glow, a diffuse signature of the galaxy's frantic stellar activity that we've simply never thought to look for in this way before. Perhaps the most exotic theory reaches beyond normal matter altogether into the realm of the universe's greatest mystery, dark matter. While it remains a highly speculative idea, some scientists have proposed that the unexplained gamma-ray signal could be the indirect fingerprint of dark matter particles annihilating with one another. According to certain models, when two dark matter particles collide, they could annihilate each other in a burst of energy, producing standard model particles like electrons and protons, and their antiparticles, which would then go on to produce gamma rays. If this is true, then the faint, uniform glow enveloping the Pinwheel Galaxy isn't a sign of stellar processes at all, but a direct glimpse into the invisible dark matter halo that surrounds it. The intensity and distribution of the glow could even help us determine the mass and cross-section of these elusive particles. While this remains a long shot, it illustrates the depth of the mystery. The gamma-ray glow could be anything from a new type of stellar physics to the first faint signal from the dark universe itself, a constant, high-energy whisper waiting for us to finally understand its language. But the enigmas of the Pinwheel Galaxy reach down to the most seemingly mundane of its components, the tiny specks of interstellar dust floating between its stars. This dust, a mixture of silicate grains and carbon-based soot, might appear to be a simple cosmic afterthought, but its behavior holds vital clues about the galaxy's energy balance. When astronomers measured the temperature of this dust across the pinwheel, they expected a predictable pattern. The dust should be hottest near the brilliant young stars pouring out ultraviolet radiation and should cool steadily with distance from these powerful energy sources. The reality, however, defies all expectations, creating a puzzling disconnect known as the dust temperature paradox, mapping the galaxy in the far infrared spectrum, which directly traces the thermal glow of these warm dust grains, reveals a bizarre and counterintuitive landscape. Vast clouds of dust located far from any obvious heating source, deep in the quiet outer reaches of the spiral arms or even in the faint halo, are shining with a warmth that they have no right to possess. Conversely, some dust clouds nestled right next to ferociously bright star clusters are cooler than our models insist they should be. It's as if you walked into a room and found a pot of water boiling on a cold countertop while a pot sitting on a lit stove remained stubbornly lukewarm. The standard rules of physics, where an object heats up when energy is applied to it, seem to be breaking down, or we are profoundly misunderstanding the nature of the dust itself. This paradox forces a re-examination of the very particles that make up this cosmic haze. One compelling theory suggests that the dust grains in the Pinwheel Galaxy are not all the same. We tend to think of interstellar dust as a uniform substance, but it likely comprises a rich population of different sizes, shapes, and chemical compositions. Perhaps the galaxy is filled with an unusual abundance of incredibly tiny, nanometer-sized grains. These specks are so small that they cannot hold onto heat effectively. When they absorb a single photon of energy, they heat up almost instantly to a high temperature and then cool down again just as fast. Our telescopes, which take time to collect light, would see the combined signal of this rapid flickering and record an average temperature that seems anomalously high for its location, explaining the unexpected warmth in seemingly empty regions of space. An alternative and more dramatic explanation points to an invisible energy source. The usual suspect for dust heating is starlight, particularly the high-energy ultraviolet photons from massive stars. But what if another, more exotic form of energy is at work? The galaxy's chaotic magnetic field could be playing a direct role. If electrons and other charged particles are being accelerated to high speeds by magnetic processes, they could collide with dust grains and transfer energy directly, heating them up from within in a way that is completely decoupled from the ambient starlight. This would mean our entire understanding of the interstellar energy budget is incomplete. We're missing a whole column in the ledger, a hidden source of power that is flooding the galaxy and warming its dust from the inside out. The implications of this paradox ripple outward, affecting almost every other observation we make. Dust is not just a passive component, it plays a crucial role in the cycle of star formation. It shields dense gas clouds from disruptive radiation, allowing them to cool and collapse. It catalyzes the formation of complex molecules on its surface, the very building blocks of planets and life. If we cannot accurately model how dust absorbs and re-radiates energy, then our estimates of the true rates of star formation, the masses of distant galaxies, and even the chemical enrichment of the universe are all built on shaky ground. The Pinwheel Galaxy's unexpectedly warm dust is therefore a quiet, pervasive challenge, a hint that in the dark spaces between the stars, the most fundamental processes of energy transfer are still waiting to be fully understood. Woven through the vast expanse surrounding the Pinwheel Galaxy, astronomers have charted faint, ethereal rivers of stars' stellar streams that trace delicate arcs across the darkness. These are the ghosts of galaxies past, the final dissolving remains of smaller satellite galaxies that were torn apart by the pinwheel's immense gravitational pull and slowly consumed over billions of years. In most cases, these cosmic fossils tell a clear story. By studying the motion, brightness, and chemistry of the stars within a stream, scientists can rewind the clock, identifying the specific dwarf galaxy that was destroyed and pinpointing when this act of galactic cannibalism occurred. But the streams encircling M101 are different. They are storytellers that speak in riddles, their narratives contradictory and their origins shrouded in confusion. The most perplexing aspect of these stellar rivers is their sheer age. By analyzing the types of stars that make up the streams, a population almost entirely devoid of young, blue stars and dominated by ancient, red suns, astronomers can estimate how long ago their parent galaxy was disrupted. The evidence suggests a profoundly ancient dissolution, an event that transpired many billions of years in the past. This immediately creates a conflict with the galaxy's other observed features. The pinwheel's lopsided arms, its disturbed hydrogen gas, and its generally dynamic state all point to a much more recent history of gravitational disturbance, perhaps within the last few 100 million years. It's as if geological evidence showed a mountain range was formed by a cataclysm last century, while the fossils found within its rock were from the dawn of complex life on Earth. The timelines simply do not align, suggesting two completely separate chapters of violence. This age discrepancy leads to a second, even deeper mystery: the identity of the victim. When researchers use the star's trajectories to project the streams backward in time, attempting to locate the point in space where the devoured galaxy once resided, they find nothing. There is no known dwarf galaxy in the vicinity that fits the bill, either as a remnant core or as a nearby object on a collision course. Furthermore, the chemical fingerprint of the stream stars adds another layer of intrigue. Their metallicity, the abundance of elements heavier than hydrogen and helium, is unexpectedly high for such an ancient assemblage. This implies the devoured galaxy was itself unusually mature and chemically enriched, having forged many generations of stars before its destruction. It was no primitive, gas-rich dwarf. It was a developed, evolved system in its own right, which makes its complete absence from the current galactic neighborhood all the more strange. Faced with this dead end, astronomers are forced to consider more exotic explanations. One compelling theory is that these streams are not the remnants of a single, cohesive dwarf galaxy, but the shredded debris of multiple smaller objects. Perhaps the Pinwheel's gravitational field captured a tightly knit group of ultra-faint dwarf galaxies so small and dim they would be nearly impossible to detect at this distance, and consume them all in a single, protracted event. The resulting stellar streams would then be a tangled mixture of different populations, creating a combined signal that appears oddly coherent yet chemically and dynamically confused, a cosmic cocktail that defies a simple recipe. Another, more radical idea involves the invisible architecture of dark matter. The movement of these streams is dictated not just by the gravity of the Pinwheel's visible stars, but by the shape and pull of its massive, unseen dark matter halo. If that halo is as irregular and lopsided as other evidence suggests, its gravitational tides would have shredded any incoming satellite galaxy in a unique and unpredictable way. The stellar streams we see today might not trace the orbit of the original dwarf galaxy at all, but instead chart a complex path through a distorted gravitational landscape, their appearance and location telling us more about the hidden dark matter than about the visible victim. These faint rivers of stars are more than just relics of past violence. They are active probes, their very confusion serving as a unique diagnostic tool for forces we cannot see, mapping the invisible contours of gravity that shape the galaxy's history in ways we are only beginning to decipher. Yet another layer of the Pinwheel Galaxy's mystery extends far beyond its star-filled disk and into the most tenuous and energetic part of its anatomy, its corona. Enveloping the entire visible structure is a massive, spherical halo of searingly hot gas, an atmosphere of plasma so immense it stretches for hundreds of thousands of light years into the intergalactic void. This is the galactic corona, and by studying its faint X-ray glow, astronomers can measure its temperature and composition. What they've found is deeply puzzling. The gas is not just hot, it is anomalously hot, with temperatures reaching tens of millions of degrees in regions where standard models predict it should be significantly cooler. Furthermore, its chemical makeup is all wrong. It is suffused with heavy elements like oxygen, neon, and iron, the ashes of countless supernova explosions, but these elements are distributed in ratios and concentrations that defy our understanding of how a galaxy ejects and mixes its enriched material. This presents a direct challenge to our models of galactic feedback, the crucial process by which a galaxy regulates its own growth. The primary engine for building a corona is thought to be the combined fury of supernova and stellar winds. These forces act like a cosmic pump, driving hot, metal-rich gas out of the star-forming disk and into the halo. As this material travels outward, it should expand and cool, eventually falling back onto the galaxy in a vast circulatory system known as a galactic fountain. The Pinwheel's corona defies this elegant model. Its intense and uneven heat suggests an extra energy source is at work, one powerful enough to reheat the gas on a colossal scale and prevent it from cooling and raining back down. It's as if the water pumped out of a fountain was somehow boiling violently high in the air, refusing to fall back to the ground. Identifying this mysterious heat source is a primary focus of research. One compelling theory points back to the galaxy's turbulent history. The same gravitational encounter that distorted its spiral arms could have sent powerful shock waves reverberating through the entire galactic halo. These waves would have traveled through the coronal gas, compressing and heating it to incredible temperatures, much like a sonic boom heats the air. The energy from that single ancient event might still be echoing through the corona today, maintaining its feverish state billions of years later. Another, more continuous possibility involves the galaxy's frantic star formation. The sheer density of supernova in the Pinwheel's active arms could be driving a superwind of such immense power that it violently shocks and heats the halo gas at its leading edge, creating a permanent, seething front of energy that envelops the entire galaxy. Perhaps the most intriguing possibility involves the invisible hand of dark matter. Some highly theoretical models suggest that dark matter particles, upon colliding with each other, could annihilate and release energy. If this process is occurring within the Pinwheel's massive and clumpy dark matter halo, it could provide a faint but pervasive background energy source, gently and steadily reheating the coronal gas from within. While this remains speculative, it illustrates the depth of the mystery. The explanation could require entirely new physics. The anomalous corona is more than just a hot atmosphere. It is a balancing act between heating and cooling, between explosion and accretion. Understanding why it's so hot and so strangely enriched is key to predicting the galaxy's future. This seething halo represents the final destination for the heavy elements forged in stellar furnaces, and its state determines whether those elements will ever return to fuel new generations of stars and planets or be lost forever to the intergalactic void, a permanent testament to the violent and confounding forces that govern a galaxy's life. And now we encounter a phenomenon that strikes at the very nature of causality within a galaxy, a mystery of cosmic choreography playing out on an unimaginable scale. Across the vast expanse of the Pinwheel Galaxy's spiral arms, separated by tens of thousands of light-years, astronomers have observed regions of intense star formation that appear to ignite in near-perfect unison. This isn't the slow, creeping spread of star birth we expect, like a row of falling dominoes. It's more like multiple strings of firecrackers set off in different cities, all exploding at precisely the same moment. This synchronized stellar ignition presents a profound challenge to our understanding of how star formation propagates, suggesting a form of galactic-scale coordination for which we have no clear explanation. Our standard model for this process is one of local, triggered star formation. A massive star forms, lives its short, violent life, and dies in a supernova explosion. The powerful shockwave from that detonation then travels outward, compressing nearby gas clouds and triggering the collapse of new stellar nurseries in a relatively small, localized bubble. This is a beautifully simple and well-documented chain reaction, but it operates at a snail's pace on a galactic scale. The shockwaves travel at a tiny fraction of the speed of light, meaning it would take them millions of years to traverse the distances between these widely separated yet synchronized star-forming regions. The fact that these events are happening almost simultaneously means they cannot possibly be causally linked by any known physical process that travels through space. The left hand of the galaxy cannot know what the right hand is doing, and yet somehow they are clapping in perfect time. This baffling synchronicity forces astronomers to consider far more exotic and powerful coordinating mechanisms. One compelling theory points to the galaxy's mysterious dark matter halo. If this halo is indeed as massive and dynamically active as other evidence suggests, it could be undergoing large-scale oscillations or density waves of its own. Just as a gravitational density wave creates the spiral arms in the visible disk, a similar wave moving through the dark matter halo could exert a gentle but immense pressure across the entire galaxy at once. This pervasive gravitational nudging could simultaneously push countless distant gas clouds over the threshold of collapse, igniting star formation in a coordinated flash that appears timed from our distant vantage point. The dark matter in this scenario would be the unseen conductor of a galactic orchestra, its gravitational baton cueing star formation on a scale we are only beginning to perceive. Another fascinating possibility involves the galaxy's magnetic field, but in a role far grander than we've previously imagined. We've already seen that this field is chaotic and powerful, but what if it is also incredibly rigid? A sufficiently strong and well-ordered magnetic field can act like a cosmic skeleton, connecting different parts of the galaxy with near-instantaneous magnetic tension. If a dramatic event occurs in one location, like the infall of a gas cloud or the eruption of a supernova, the resulting disturbance could travel along these magnetic field lines at Alfvén waves, a type of magnetic ripple that can propagate very quickly. This could allow a signal to effectively bypass the slow drift of gas and travel much faster across the galaxy, delivering a triggering impulse to far-flung regions almost in unison. The magnetic field would become a galactic nervous system, allowing for a rapid, coordinated response that defies the slower laws of hydrodynamic motion. A third and perhaps most dramatic theory looks beyond the pinwheel itself. The synchronization might not be an internal process at all, but an external one. The galaxy is not floating in complete isolation. It is part of a local group and moving through the intergalactic medium. It's possible that the entire Pinwheel Galaxy recently encountered a massive and diffuse cloud of intergalactic gas. As the galaxy plowed into this cloud, the resulting ram pressure could have uniformly compressed the gas across the entire leading face of its disk. This would have been a galaxy-wide event, like a submarine experiencing a change in water pressure along its entire hull simultaneously. This single external trigger could have initiated a surge of star formation that, from our perspective, appears perfectly synchronized across vast distances, a testament to the fact that a galaxy's evolution is not always a story of internal dynamics, but can be dramatically shaped by the environment of the intergalactic sea it sails through. Unraveling this mystery is more than an academic exercise. It forces us to see a galaxy not as a collection of independent regions, but as a single, interconnected system where the largest and most invisible forces, be they dark matter, magnetism, or intergalactic weather, can dictate the rhythm of creation itself. And now we arrive at a mystery written not in the birth of stars, but in their final, beautiful breaths. As sun-like stars reach the end of their lives, they don't go quietly. They undergo a magnificent transformation, puffing off their outer layers into space to form a brilliant, often intricately structured shell of glowing gas. These are planetary nebulae, the glittering funeral shrouds of intermediate mass stars, and they are one of the most visually stunning and scientifically valuable phenomena in astronomy. They serve as crucial markers, allowing us to trace the population of dying stars and understand the chemical enrichment of a galaxy. In a vast, mature spiral like the pinwheel, teeming with billions of stars of the right age and type, we expect to find thousands of these cosmic butterflies. But when astronomers go looking for them, they come up almost empty-handed. The number of confirmed planetary nebulae in M101 is startlingly, inexplicably low, a profound deficit that suggests the galaxy's stars are dying in a way we simply don't understand. This missing population is far more than a simple headcount error. The expected number isn't a guess, it's a calculation based on the well-established relationship between a galaxy's total stellar mass, its star formation history, and the predictable rate at which stars of a certain mass die. The Pinwheel Galaxy, for all its splendor, is failing this basic test of stellar demographics. It's as if you were to walk through a vast forest known for its vibrant autumn colors, only to find the ground curiously bare with almost no fallen leaves. The trees are there, the season is right, but the expected transition simply isn't happening. This forces us to confront a handful of unsettling possibilities, each with dramatic implications for how stars end their lives. One leading theory is that the interstellar environment in the pinwheel is simply too hostile for these delicate structures to survive. A planetary nebula is a transient phenomenon, a cosmic soap bubble that may only shine brightly for a few tens of thousands of years before it expands, dissipates, and fades into the general interstellar medium. In a galaxy as dynamic and violent as the pinwheel, with its powerful supernova-driven winds and intense ultraviolet radiation fields, these fragile bubbles might be getting shredded and destroyed almost as soon as they form. The fierce radiation from nearby young star clusters could photoevaporate the nebula's gas, tearing the atoms apart faster than they can radiate their characteristic light, while shock waves from stellar explosions could smash the intricate structures into a chaotic and unrecognizable mist before our telescopes ever get a chance to see them. Another, more profound possibility is that the stars themselves are different. The formation of a visible planetary nebula requires a precise and delicate dance between the dying star and its ejected envelope. The star's core must heat up at exactly the right rate to flood the expanding shell of gas with enough ultraviolet radiation to make it glow. If this process is off, if the star ejects its envelope too slowly, too quickly, or with the wrong chemical composition, the nebula may never achieve the brilliance needed for us to detect it from 21 million light-years away. Perhaps the initial mass function in the pinwheel is skewed, producing fewer stars in the precise mass range that leads to a classic planetary nebula. Or maybe the metallicity of the stars, their abundance of heavy elements, affects the physics of the mass loss process in a way that results in fainter, shorter-lived nebulae that escape our surveys. The stars might be dying, but they are doing so in a whisper rather than a shout, leaving behind dark, expanding clouds of cold gas instead of brilliant, glowing monuments. The most fascinating implication of this absence touches on the entire cycle of cosmic rebirth. Planetary nebulae are the primary mechanism by which stars like our Sun return their enriched material carbon, nitrogen, oxygen, and other elements crucial for planet formation and life back to the galactic ecosystem. If this process is being suppressed or is operating inefficiently in the Pinwheel Galaxy, it could mean that the interstellar medium is being starved of these critical building blocks. The galaxy's future generations of stars and planets might form from raw material that is curiously deficient in these heavier elements, potentially altering their evolution and the very possibility of life arising around them. The missing planetary nebulae are therefore more than just a curiosity. They are a potential break in the circle of stellar life, a silent hint that the beautiful death of a star is not a universal constant, but a process deeply sensitive to the unique and mysterious environment of its galactic home. But perhaps the most visually striking of all the pinwheel's enigmas is one that manifests not as a presence of light or energy, but as a profound and unsettling absence of it. Woven throughout the galaxy's spiral arms is a vast, intricate network of dark nebulae clouds of cosmic dust so incredibly dense and opaque that they blot out the light of the stars behind them, carving black silhouettes against the galaxy's luminous backdrop. From our distant vantage point, they appear as inky rivers and tendrils, a complex web of shadows stretching across the stellar tapestry. Yet these are not merely larger versions of the dark nebulae we see in our own Milky Way, like the famous Horsehead Nebula. Their sheer scale, their peculiar structure, and their bizarre physical properties mark them as something entirely different, a population of interstellar obscuras that defy all our expectations for how such simple clouds of dust and gas should behave. The first and most glaring anomaly is their incredible darkness. A typical dark nebula is only dark in contrast. It's a relatively thin cloud that dims the light from background stars, making them appear redder and fainter. The filaments in the Pinwheel Galaxy, however, achieve a level of opacity that is almost absolute. They create voids of pure blackness where the stellar background completely vanishes, suggesting densities of dust grains far exceeding anything found in our own galactic neighborhood. It's the difference between a thin morning mist that softens the landscape and a thick, impenetrable fog that swallows all light. This incredible density immediately raises a fundamental question. What physical process could possibly compress and contain so much dust into such tight, coherent structures without it collapsing to form new stars? The natural tendency for a cloud this dense would be to fragment under its own gravity and ignite a firestorm of star birth. Yet these clouds remain eerily quiescent and stable, hoarding their immense mass in darkness. Their morphology is another radical departure from the norm. Instead of the amorphous, blob-like shapes of typical dark clouds, the Pinwheel's network exhibits an almost fractal-like complexity. They form long, filamentary chains, intricate loops, and interconnected knots that look less like accidental accumulations of dust and more like the deliberate architecture of a colossal, dark spiderweb. This highly organized structure suggests they are not passive features, but are instead being actively shaped and sculpted by powerful external forces. One compelling theory points to the galaxy's pervasive and chaotic magnetic field. The lines of magnetic force could be acting like invisible wires, trapping and organizing the dust grains, which are often slightly magnetic themselves into these long, drawn-out filaments. The entire network might be a visible map of the galaxy's invisible magnetic skeleton, with the dust merely tracing out the lines of force in a dark, dusty ink. Another fascinating possibility involves a different kind of physics altogether. The dust grains in these nebulae might not be the familiar silicate and carbon-based particles we know. They could be composed of entirely different, more exotic materials that formed under unique conditions in the Pinwheel's past. Perhaps they are much larger than typical interstellar dust grains, more like tiny pebbles than fine smoke. Larger grains would be far more effective at blocking light and would also be less susceptible to being pushed around by radiation pressure from nearby stars, allowing them to clump together into more massive and stable structures. Alternatively, the chemistry on the surface of these grains could be different, allowing them to stick together more effectively upon collision and build up these massive, dark aggregates without spontaneously collapsing into stars. The most significant implication of this dark network is its impact on our very view of the galaxy. These nebulae are not minor features. They are massive obscuring agents that block our line of sight to huge portions of the Pinwheel's disk. This means our census of its stars, our measurement of its star formation rate, and our understanding of its true structure are all potentially skewed. We could be missing entire star clusters and stellar nurseries hidden behind these dark curtains, fundamentally misjudging the galaxy's activity and evolution. The dark nebula network is a stark reminder that what we see in a galaxy is only the part that is illuminated and visible. A vast, hidden geography of dust and shadow exists just beneath the surface, a dark counterpart to the glittering spiral arms that challenges us to question the completeness of our observations and to wonder what other secrets might be hiding in plain sight, shrouded in a darkness so deep it has become a mystery in itself. So after this journey through 30 of the strangest celestial secrets, what are we left with? The Pinwheel Galaxy is far more than a beautiful face in the cosmos. It is a living, breathing challenge to our fundamental textbooks. From its missing black hole and phantom dark companion to its chaotic magnetism and rebellious stars, each phenomenon we've explored isn't just an isolated curiosity. Collectively, they paint a portrait of a galaxy that refuses to follow the standard rules of astrophysics. This isn't a system quietly winding down. It is a dynamic, turbulent, and incredibly complex entity whose history is written in violence. Its present is governed by unseen forces, and its future is shrouded in mystery. Every strange observation, every unexplained signal, is a direct question posed to our models of galaxy evolution, dark matter, and stellar life cycles. The Pinwheel Galaxy stands as a monumental reminder that for all our advanced technology and sophisticated theories, the universe remains masterfully adept at surprising us, forcing a humble and continuous re-evaluation of what we think we know. This beautiful enigma, floating 21 million light-years away, is not an obscure outlier. It is a critical case study, a galactic laboratory that is actively refining our understanding of the cosmos. Its contradictions are not frustrations, they are opportunities. The missing globular clusters challenge hierarchical formation models. The inexplicable gamma-ray glow hints at new particle physics or dark matter interactions. The synchronized star formation suggests coordination on a scale we can scarcely comprehend. Each mystery is a thread in a larger tapestry, and pulling on any one of them threatens to unravel entire sections of our cosmological understanding. The Pinwheel Galaxy proves that maturity in a galaxy does not mean simplicity or quietude. It can mean a deeper, more layered, and more confounding complexity. It pushes us to look beyond the visible, to question the inertia of established theories, and to remain open to the possibility that the universe is far stranger and far more wonderful than we have yet dared to imagine. Now we've covered a lot of ground, or rather, a lot of space, and I'm incredibly curious to hear which of these 30 phenomena captivated you the most. Was it the ghostly dark galaxy hiding beside it, the terrifying hypervelocity runaway star, or the inexplicable diamond-shaped core? Jump down into the comments and let me know what stuck with you. This conversation about the cosmos is a collective one, and your perspective is a vital part of it. If you enjoyed unraveling these mysteries with me and want to explore more of the universe's deepest puzzles, make sure to hit that subscribe button and tap the bell so you don't miss our next journey into the unknown. Until next time, keep looking.